Hello all. So this video is a re-recording of the Week 10 video, and this is because the last video which I had uploaded due to some technical problem, uh, uh, the video was not working properly, and it was came to my notice a bit later. So yeah, let me start with Week 10's materials and what I had done in the last Week 10, and I'm going to upload this in YouTube. So the first question is this, just so we've been given the harmonic oscillator, given the Hamiltonian the harmonic oscillator is which is this. The first question is to write H in second quantized notation. And to write the wave functions So this is the first question. Let me just do something. So this is the question. Take a minute and then I'll start solving it. So the solution, okay, let me start. Solution for this is we need two operators, and these two operators should satisfy uh, the canonical commutation relations. That is, xp is equal to IH cut. So our job is to change xp to a new variable. So the job is to change xp to a new variable, which shall call a and a dagger, such that the commutation relation is intact up to some factors. So actually, we remove the factors of IH by redefining A and by redefining XP as A and A dagger, such that IH goes away, but you're always going to get a kind of structure which is like that. And in this in this redefinition, we would also have something that helps us, to. So, for example, this is the lowering operator and this is the raising operator. And so it helps us to create more states starting from a base state. We would also want that. So to do this, we're going to choose. By the way, this is a bosonic simple harmonic oscillator. That means these has to satisfy these commutation relations. These are also going to satisfy the commutation relations, not the anti-commutation. So write A as A dagger as I just want to check if it is recording or not. Okay, it is. We have this. Now I'm going to, okay, beforehand, we don't know what this commutation relation is, right? So, but we know that, that it has to be one combination of this or the other. So, it's more like, what you find when you calculate. But with this, you can directly go ahead and you will check. This comes out to Hn omega omega x psi p minus I p. Now, since this and this is 0, we have only the cross terms. So the first term is now while calculating commutation relations, the constant factor which are not operators, they come out. So m omega, they come out and I also comes out. So I'm going to have I m omega, so which is equal to 2h cut. Now px we know is px is minus h cut because as we know the commutation relation is antisymmetric. So this is minus I h cut minus, and this is plus I h cut p. So we're going to get this, which is minus 2 I h cut and p h cut. Right. Hence we get 1. This cancels, and I square is just minus 1. Minus 1 into minus, which is already here, we get 1. So now the second thing to do is write the uh, write the Hamiltonian in the this canonically in the A dagger language. So for that, we'll try to derive what A and P is, what X and P is from this equations. So X is going to be just no. We add A plus A dagger by 2, going to get M omega by 2 H cut X. That is 2 H cut. This is 1, and P is equal to A minus A dagger by 2I 2H cut M omega. Now, therefore, the Hamiltonian, which is E square by 2M half M omega square X square. You just substitute these things, which gives us minus A dagger by 2I square. So this gives minus, because there's a I, and 2H cut M omega by 4 times 1 by 2M minus A dagger square plus 1 by 8 M omega square. There's also M omega by 2H. Sorry. 2H cut by M omega. So then this will be 4 to the 8 and 1 by 8 omega and omega square 2H cut by M omega A plus A dagger square is equal to H cut by 4. This is also equals H cut omega by 4. A square plus A dagger plus A dagger A plus square minus a square minus, it's going to be plus a dagger plus a dagger a minus dagger square. So this is because since these are operators, and you're going to get this thing instead of, since these are operators, they do not commute as we have seen from the commutation relation. So I can't just write them as 2A dagger A or something like that. This is what is going to happen. So this and this gets cancelled, this and this they get cancelled, and I've got is now using commutation relations. What I'm going to write it is I'm going to write it in terms of the A dagger A. We have the commutation relation equals 1, which means that A dagger A is equal to A dagger minus 1. Sorry, I want to write it in terms of I want to write it in terms of A dagger A. Then I'm going to get A dagger A. Then so I want to substitute A dagger. So from here, A dagger is just A dagger A plus 1. Therefore, I'm going to substitute it again. I'm going to get HS is equal to, that is it. We are done. This is the Hamiltonian in the second quantized notation. There's no quantization taking place, but this is what they consider as second quantized notation because of analogies in the field theories when we do. So for the wave function part, we have to define a vacuum. And this definition of vacuum is such that the lowering operator acting on vacuum gives 0. Therefore, we will say that 1 at 1 is gotten by using the raising as such. This is the first excited state. Yeah, before doing that, yeah, let me tell you what's 1 and all. So we have defined this. Now, using the commutation relation, A dagger minus A dagger A equals 1. you're going to see what happens to the vacuum. A dagger acting on 0 is equal to 0. This is just a one unit operator. So A dagger acting on 0 is equal to 0. Okay, this is the logic. That means this is not 0. Uh, this whole of it is giving something. It's not 0. It's not 0 the number. It's the vacuum. So when I say 0, I mean the number. 0 means the number. No? Vacuum means vacuum or ground state. So now, so then we say that, so we are going to think of this thing as like this. This cannot be 0 itself. This is uh, this is a new state, which when acted by A is gives the ground state, and we know such a thing by defining this thing as the number operator, A dagger A as the number operator, and working out the commutation between this and H. We, with H and also with these two, the commutation between these two, we know that A dagger raises the vacuum state by and takes it to the first excited state. So the first excited state is given as like this. Now, if you work A on it, you are going to get the ground state. That's why we are getting this same thing after action of A. Two is you act it again, but now you also require a normalization. Normalization of this thing is again found out using the commutation relation, and you get this. So your get n is just A dagger acted on n times and square root and factorial. Okay. I haven't gone into a lot of details, but uh, if I want to tell naively to you, I can say that so one will see in my later lectures that one can now I'll give a justification. Is indeed the nth state that is all normalizations written above also agrees. So that I'll pose it as question number, Mm, I'll pose it as a new question, and I'll call this question 1AB, question 1C. One can formulate, right? So this is the information I'm giving you, and this is true. One can formally write A as DD A dagger. Okay. This is this I have shown in. Let me just see if I've shown it here. Later assignment. Using this and expression of K10 show. So, so we know that this is correct, and this I've shown later, and we want to say that the expression of n is correct. So I'm going to show this happens for this state, and using this, then we are done. We know that we surely for know that this is right. Solution goes as like this, acting on K10. You're going to find this equals mhm. Now this is just normal differentiation of a dagger. So you just differentiate this. So you're going to get something like this. And from here, you are going to get n plus 1 n minus. So this n is just a number, so this can come out, and this is going to go and uh, get multiplied with that one. So we are going to get this. So you can see that we have got this whole term, which is the same. And this is just n plus 1 minus n times this thing. So we have got 1 times n plus 1 minus n, which is 1. Which completes our proof. Thus we showed that there is 1 for Therefore, we have shown this. That means that the expression for cat n is correct. This is one of the faster methods which I like. That is why I do it in this way, this formal way of writing. So yeah, just check. Okay. 30 minutes are gone, and let's go to next problem. So this problem was not presented earlier, but anyways, I just quickly showed it. Let's go to the second question. Second question is that second part A. Find the spin operators the expression of it in second quantized notation for a spin half particle in the part A, and part B part B is find Sx, Sy, Sz explicitly. Second quantized notation. Okay. Solution to it is so our spin operator is given as, and right now I'm not okay. I'll write the factors, which is h cut by 2. This is the Pauli matrix X, Pauli matrix Y, Pauli matrix Z, where they have their usual definition. Okay. Now what we want to do is we want to do some kind of second quantization or some kind of a Fourier transform in this case. Okay. So we want some kind of a, so whenever we go to second quantized notation, I just want to remind you, suppose we have got psi, which is a position space. We write e4x, now e power ikx, ak plus and this is what we do. We have wave function and it is already quantized system, and then we are writing in this basis, and we'll find what happens to the what's the relation between this and this. That is, find the commutation relations starting from the commutation relations of whatever we have here. Okay, this is for field theory basically. So whatever I'm saying is for field theory. Okay. So you're going to have commutation relations between momentas and the fields, for example, and this has got something here. Using this information, we're going to find something about AK and AK daggers. Okay. We're going to find something here. This is the idea in the way it works. And this thing is given by the idea of this thing is gotten by you've got your classical bracket. which is the Poisson bracket between these two fields. And when you quantize them by saying that, now we have got a Hilbert space, you're going to change the Poisson bracket to the commutator. So this is the idea of the canonical quantization. So, so this is classical mechanics. The quantization. This is the canonical quantization idea. This is in quantum mechanics or quantum field theory. And using this in second quantized notations. Mind you that there is no second quantization in the terms of like quantization happening. We are not again performing a quantization while going from here to here. This is just a notation. And we say that this is second quantized notation. Okay, so this is what we are doing. So we need to find something analogous to spin, which we are doing for psi. That is what I wanted to get at. And that is actually given by, you need to keep track of every indices. The S, which can be written as sum over, since these are discrete variables, so we will sum over mu and sigmas, mu prime, sigma, mu, let me just give you back in a moment. Yeah. So this mu can be thought of as some kind of uh, mm, what do you say, a position, okay? And this sigma prime can be thought of as upspin or downspin. These are the eigenvalues of this. The sigmas are up or down. For a spin half particle, sigmas can be up or down, which is denoted by this index, and mu is the position actually. And this can be written as, for mu and mu prime, which are the same, this can be written as S mu and you have your S vector here. So S vector, I have opening and writing it. This is for the second question actually. So here we are assuming that mu and mu prime are same. Okay? Mu and mu prime are same. So that is why this summation, it gives you a Dirac delta of mu prime, and you get, so you're looking at the same position. So you are getting mu prime are same, and they give you a Dirac delta. Okay, they don't operate on this. That means this is independent of any mu index. Okay, so mu and mu prime will give you delta mu prime mu, and you'll have mu prime is equal to mu here. So that is what I have written here. and then it's just a summation over mu because of the delta collapsing the mu prime. Okay, now let's go to part B. So we need to find Sx, Sy, Sz explicitly. Okay. So let's do for Sx and you'll understand how to do it for Sy. So for Sx, you're going to choose this matrix, and these are the various combinations of ups and down spins which you can have. Okay. So yeah. So if you write these things in terms of like term by term notations, like then you're going to have a well, let me explain what I mean. You just do this up and down, make a vector like this. Yeah. So this vector, like this, and you write the matrix. This is a clever way to, do this without getting into too much notational trouble. Just write it as a vector of eigenvalues. In fact, this is going to be that only. What I'm doing here is I'm collapsing. So from this step to this step, I have collapsed this and I've written it in terms of vector, and this also as a vector, and this as a big matrix. And the reason I'm doing this is because this is easier to write. Otherwise, you would have to take every sigma, and for that every sigma, you would have to look at one of the index of these things. For example, this multiplies with this, and this multiplies with some term which is going to come in this vector. You will have to do that summation term by term, and it's a bit confusing. So notation wise, there are some, so this also should have like, yeah, this also, there should be some notations here also, which tells you which this I'm multiplying, but this one helps you a lot. This gives you directly what, what you want to say. So up, down, okay. Mu, sigma dagger. Okay, only the non-zero ones we are going to uh, only the non-zero ones are going to come here. That is the idea. So in fact, this also I shouldn't have written because it's already okay. I can write that it's already collapsed actually. But for notational convenience, I'm doing this. So let us multiply this and see. This is going to give okay. Now this is what we are going to put here. That is, now our Sx is equal to h cut by 2 summation over mu, and this is what you're going to put here. That is mu down dagger mu up plus c mu up dagger mu down. This is what is Sx. Similarly, you do for Sy. For Sy, you're going to look at the matrix. You're going to look at you're going to calculate this. So you have minus I up down plus I down up. Therefore, Sy can be directly written as h cut by 2 sum over mu minus I c mu dagger up c mu down plus I c mu dagger down c mu up. Take I out and write this properly. You're going to have c mu down dagger c mu up minus c mu up dagger c mu down. This is Sy. For Sz, you're going to have up down 1 0 0 minus 1 up down, which is up down up minus down, which is up minus down down. Therefore, Sz is going to have h cut by 2 over mu c mu up dagger c mu up minus c mu down dagger c mu down. Actually, a better way to write this notation is, instead of doing this, this notation should have been written like this. Okay, this is the best way. C mu up dagger, C mu down, mu up dagger, C mu down. Is this right? Well, this is what I have. C mu up. When I take a dagger, it should be down. When I take the dagger is going to come here. Okay, so I'm going to get C mu is right, up down down up down. So I should get C mu dagger down, C mu. Yeah, this is the correct way to write it. Yeah, this is right. This is notationally correct. Yeah, yeah, right. That is correct. Okay, with this we are done. Let us do the third problem, which is we want to do the same this thing for the kinetic energy. Yeah, we want to do the same thing for the kinetic energy. And the kinetic energy, question number 3 is, find the kinetic energy in second quantized notations. Okay, so kinetic energy is given like this. So kinetic energy T of R sigma prime sigma is given as minus h cut square by 2m. So this is just p square by 2m. Okay, sigma prime sigma is there because to depict the spin notation. Right? So this is what. So if it is up spin and down spin, the kinetic energy is 0. If it's up spin, it's the same. There is some kinetic energy. And this has been written in the operator form in the position space basis. Now we have to take its Fourier transform and get the momentum space basis, and that will tell you, as I had written here. So we have the kinetic energy in the position space basis. We are going to take the Fourier transform to get it in the momentum space basis, and that's it. We are done. That is what we have to do. For k is equal to integral dr or minus ikr tr sigma prime sigma. This can also be written in terms of the bracket notation as like this. So this where this k is equal to some k tilde I am writing. Tilde is equal to k minus k prime. Okay. Here, in other words, let me do it like this. This is kind of wrong to do. Tk is actually dr or minus ikr. Okay. K prime r in fact. dr e power ikr. Okay, let me write it in bracket notation. Hmm. So what I was trying to do was, if I want to find the position space this thing, so I'm going to insert this here. I'm going to insert this here. I'm going to not only insert this, so I'm going to insert a closed set of states. What I mean is this dr prime, and this is going to give, this is between position and momentum. So e power I k prime r prime. There is a sigma index which I am giving. So sigma index, okay, I'll keep the sigma index. And this is what I have, which is r prime. So this thing, this operator is in the position basis. Okay, in the position basis, I'm going to get minus h cut square by 2m del r square. Okay, the sigma prime sigma, and this should be, this should have a, so it's not working. Don't act in this, but yeah, just write it first. I a r sigma, and you have a Dirac delta of r prime minus r. So this gives you r k prime r sigma. So this is going to give you minus h cut square k square by 2m, and this part is uh, delta of k prime sigma delta of sigma prime sigma and delta of uh, delta of k prime k. Okay? This is how you get it. So I was trying to write this only. Hmm. Or in other words, I could have directly done it from here also. Or, maybe I could have started out with this line, by that is the, no, not this line. Yeah, this line. And saying this is the Fourier transform, which I'm doing. Especially I'm doing this only. And then go here and then go here. And then argue that this, when acts on this, we have this thing. This is the position representation, which when acts on this, you can think this is KIR. We are going to get h square k square. So you've got this. This is right. That is it. So let us go to question number 4, which is the particle density operator, which is given as rho of r is equal to in second quantized notation. Uh, okay, just an aside, which I was also saying. So, if a field theory has a U1 symmetry, that is, it is. So, if you've got a field theory, which is, say, this is a Lagrangian in 4 dimensions, look like this. This is in the 4 vector notation, d mu square. Okay, suppose phi is complex, okay, and you have a symmetry which is phi goes to e power I alpha phi. Okay, and this alpha is not a function of the position. So you can just, so d mu doesn't act on it. So you're going to see the Lagrangian is going to have, I have written this only, this Lagrangian changes to, going to get a minus E alpha d mu phi dagger d mu phi or I alpha. This and this, they are constants, so they are going to cancel. And this give you changes into same Lagrange. Okay. So this is the symmetry of the system. Since this is a symmetry, as we read in Noether's theorem, there should be a conserved charge. So this conserved charge is generally the number operator. Okay, is the number of. So it's actually something. The conserved charge, something like this. A k a dagger k a k. This thing. Something like this is constant. Okay, or in field theory language, I think it's it's a constant. That is the number of particles which has been created. The field theory interpretation is like this: that this momentum, this second quantized notations act into some state and creates some amount of particle. This gives you that the number of particles in that state is a constant. All right. So the particle density operator can also be thought of like this. This particle density operator tells you how much particle is in some state and its density. All right. So, so in this state, uh, by meaning this state, here we had this number operator which defines a state. Here you can think that there is some, at some position, what's the density of particles. The interpretations can change, okay? Is what I want to convey. And the reason I'm saying this is because sometimes it's written like this, and if it's not in the quantized notation, it is something like psi dagger psi is constant, something like this, okay? The integral of this. So this, yeah, this particle density operator is closely related to it. It's at some position because you can see that R dagger and R have to be the same, right? So this is basically probability of particles in at a position. Maybe that's a better way of saying it. But it has got an interpretation. So we are looking at the second quantized form of this. But this is an aside. This is something which uh, this thing which I've told you, it's an important thing, the conserved charge when this symmetry is preserved. And yeah, let's move forward. So we've got, so yeah, let's solve this. So what I have written is nothing but actually mod sigma mu sigma. This is just this, right? Because the Dirac delta will act and the integral will vanish. So this is going to be this. And this I had written, actually I had written this is this. Yeah, it is whatever shy. So now we want to, we know the second quantized versions of these things. The sigma index and mu is some, uh, mu is an index which we can drop for now actually. So shy has something like this. So shy dagger. So this is something like this. Now we are going to put it in row. Row of R is dr dr prime or minus ikr um, ikr and sorry, should be dk prime or minus ik r ak dagger sigma power ik prime r. So since this is shy of r and shy of r, the r's are going to be same. AK prime sigma. Okay, so dk prime e power minus I k minus k prime r ek. So this can be written as dk prime. Now remember that if our momentum values are discrete, this is going to be summation. In condensed matter, mostly people are going to write it as summation. So to follow that convention, and also this is what I used last time. So I'm going to write it as this, and there's some volume factor which is coming in, so 1 by v for that. So e power minus I, this is q, some vector q, dot r vector, and so I'm going to just change as this q, and I've changed k prime, so k is going to remain the same, and k prime is going to be k minus k prime is q, k minus q. All right, that's it. V sum over q AK dagger sigma minus Q sigma or minus IQR. Now this Q momenta is thought of as some momenta which has been transferred. Okay, where Q is equal to K minus K prime is some momentum transfer. So that means it's like there is a particle which is being destroyed. So suppose there are a lot of particle. The particle has been destroyed some position. The mu index would tell position. It's been destroyed. That means the momentum of this particle has gone down and that has been gone to some other particle. That is what this means. This part. Let us do a similar kind of analysis for the case of let us do a similar kind of analysis for the Coulomb interaction. And here we are going to get some diagrams, which we are going to naively call as Feynman diagrams. They are actually Feynman diagrams. And these are like the first order. This is even called like tree-level Feynman diagrams, where you don't have any loops or something. And we are going to understand with this example right there. Which is so I want to point out some symmetry facts of these things. That is, usually this potential is translationally invariant. That means uh, you do a plus A here, and there also plus A. This plus A and plus A, they are going to cancel, and it's going to be the same. All right. Now it's also rotationally invariant, and that rotational invariance is it's due to this mod. Okay, so the best way to see this is fix R1 as 0, R1 goes to 0, then you are going to have KE square by mod R square, where R2 I have said as R. Sorry, the KE square is mod R. Okay, now when you rotate your frame, this mod R is the distance. This mod R is the distance from here to the vector, from here to the position with the position vector R vector. Okay, and that remains the distance of that vector. It remains conserved when you are doing rotation of your axis. This is the rotation in, say, the SO3 rotation. It's called SO3. The rotation is denoted, the rotation acts on R3 by the SO3 group. Anyways, that is an aside. So these are some of the symmetries. What does these symmetries helps us do? Why are these symmetries important is the question which we are interested in. All these things which we have done we're going to see that most of them have rotational, most of them have this translational symmetry. Okay, and there is a reason for having all this translational symmetry. For example, here also in all these, except the spin has no, uh, you know, there's no idea of the translation there. So spin in x direction, y direction. So there's no. So let us start with after spin, which is the first one was kinetic energy. There is a translational invariance here also, because if you do tr plus a, you're going to just have r plus a here. This is a constant, and you in the derivatives wherever you have dr plus a, this is nothing but dr. Okay. All right. So this has got a translational invariance. This is the very heuristic way to see it. This also has got translational invariance. The way in which you can show it is, so the way in which you can show it is by looking at here itself. So you do rho of r. Sorry. Here will depend on the Lagrangian shine. Just like a redefinition. The fact is that this kind of argument which I just gave now, it's circular, because the reason is because the reason which I'm going to tell you, right? The main point of takeaway here is still this field itself, wherever I'm inventing wherever, this is still rotational limitation. Point is, so one more thing which I something, something. 3 sigma 1 dagger, K4 sigma 2 dagger, K2 sigma 2, K1 sigma 1. Now you look at the integral, and this integral can be written as so I put terms with R1 together, which is K1 minus K2, K1 plus K2 minus K3 minus K4. And there is a term like this, 2 minus K4 dot R2 minus R1 divided by minus R2. So we'll call Q as K2 minus K4 and R as R2 minus R1. Then we get I as dr. The Jacobian of transformation is just 1, okay? Thus, because R1 is here, we are only replacing R2 and R2 has a positive sign in front of it. So it's just this thing. So R1 dot K1 minus K3 plus Q vector, or I Q vector, not R vector, by mod R vector. And we're going to integrate over R1 and get Dirac delta of K1 minus K3 Q vector e power IQ vector. This is Dirac delta of K1 minus K3 plus Q times and uh, this is actually the what do you say? Yeah, this integral. If you do this integral, you're going to get 4 pi 4 pi by q square. Okay, this is delta K1. And the way to do is by some contour integration. But as far as you have seen, probably in electrostatics, when you want to write the potential in this term, if you've got the uh, what is that? The Laplace equation. If you want to write the potential, you can write it in this form. This is just with this. This is basically telling you, this is giving you this quantity is in the momentum space. All right. And the way to get it is you're going to have del square the Green's function is delta g. If you write it in the if I remember correctly, this is just e power I ar, and this g is k square times g. So yeah, this is right. K square times g. There also you're going to have this integral. Means g in the momentum space is e power I k r by k square. Now you want to write this in the position space. Yeah, you want to write this in the position space. You're going to get the position space. G of R would be something like power IKR by R mod R. You can do this integral and you can get this. So what I'm doing is I'm going the other way. This. Sorry, yeah, that is why I was confused. Should have been 1 by k square. So when you take the Fourier transform, you also have IKR here. So you don't take this. So G is just 1 by k square. You want to take the Fourier transform, 1 by k square, and you want to. So this is what we are getting. Okay, 1 by k square. This is what we have done. We've taken the Fourier transform in this language. So if I were to invert this, I am going to get G of R, which is going to look like this. If I'm going to invert this, I'm going to get this. Now, right, the full potential is right, 2V summation over sigma 1, sigma 2, K1, K2, and Q. Then we have VQ. This VQ is 4 pi by Q square. A K1 dagger plus Q sigma 1, A K2 minus Q dagger sigma 2, A K2 sigma 2, A K1 sigma 1. And we have got this. Now the interpretation of this in terms of diagrams. Okay, this is a bit important. So we'll have some particle going in the momentum space, which has got spin sigma 1 and has got momentum k1. Right? It interacts with this potential. The interaction, it interacts with this. It interacts a potential, which is the Coulomb potential, and it is mediated. This Coulomb potential is mediated by this interaction. Okay, the mediation has a value of this much. This is the best way to say it. All right, that is, it gets mediated. So you have an incoming particle. You need another also, because if you don't have that, there is no Coulomb interaction. You need two charge particles. So two charge particles are going in. One with momentum k1 sigma 1, other with another momentum sigma 2. Okay. There is a mediation happening. This is mediated by this potential VQ, which is written here 4 pi by q square. And it transfers the momentum, say, to the q1 particle, and the momentum transfer is q amounts. All right. So if the transfer happens like this, then only I'm going to get k1 plus q. Okay. Thus, a particle which was coming in, okay, interacts with the Coulomb potential, and then it gets destroyed, and in its place, a new particle gets created with k1 plus q momentum. Right? That is what this equation is saying. And the spin remains the same in this process because this Coulomb potential doesn't touch the spin at all. Now, what will happen to Q2? Since it gave a momentum this much, it should lose momentum while it's coming out. So that is what happens. It loses momentum. The momentum lost is Q. It goes out. It gets destroyed. In fact, in this interaction vertex, the best way to like interpret the equations correctly is it gets destroyed and a new particle gets created because there's a dagger sign here. because with momenta k2 minus q, and the spin remains the same because it doesn't touch the spin at all. So this is the Feynman diagram of this process. Okay, P-level Feynman diagram. So what does that mean is you've got your Dyson equation and all these things, which a professor, which is written there in Professor's book, Professor Settler's book. So this Dyson equation, this is the first order term. You're going to think that this V is a interaction term. There is a free field, which is just given by the kinetic energy, plus this V, what you have, the Coulomb. You're thinking this V as interaction term. And this interaction term, what it does is, it up to the first order in Dyson series gives an interaction of quantity this much. So, now we are going to do some problems on uh, what is it? Tight binding model. Yeah. So the question is as follows. Question number 6. So given the Hamiltonian of a tight binding model, which is minus T, which is the coupling, and the nearest neighbor interactions is denoted by angle bracket, Ci dagger Cj, plus the Hermitian conjugate of it. Find the dispersion relation, which is find energy as a function of k in k one dimensions, b two dimensions. So this bracket means that you're only going to take the nearest ing should be nearest neighbor in the lattice which you're considering. Let's do number in one dimension. We can write Ci as the square root n sum over k. So this is the position index. We're taking it into momentum index. This is a k one ri k one. Similarly, when you write Cj, you're going to have a different this thing k2 k2 rj ck2. Therefore, our h is okay. This is very general. This is not in one dimension. No. This is in one. So I guess it's better to do before doing dimensions. I'll write the general formula. General, and then we'll go to one dimensions. So if you do something generally, you're going to have in any dimension, this is going to be vectors and there is going to be a dot product. All right. Where where in two dimensions, it would mean that your k vector is ki vector is or k1 vector is k1 x and k1 y. Okay. Where your ri vector means ri x ri y. Okay. So now the Hamiltonian is going to look like minus t by n sum over k1 is a vector, remember, k1, k2, okay, e power I k1 ri plus k2 rj. C dagger k1 vector c k2 vector. And also there is a angle bracket. So this is the general Havelland. Now let's go to one dimension and see what happens. Just on this side. CI dagger CJ. So yeah. So now part A, one dimension. If it is one dimension, okay, and if I've got an I particle, the next nearest will be I plus 1 or I minus 1. Okay? I will consider only I plus 1 because when we consider I minus 1 particle, we have already considered I minus 1 and I's interaction. All right. So we are going to put a j is equal to I plus 1 and every interaction is going to come twice. If you have this interaction and you have the other interaction which comes from the Hermitian conjugate. Yeah. So remember, there is also a Hermitian conjugate here. Like C dagger J Ci. So C dagger J Ci would mean also considering the other way around. Considering this, you're considering this also. That is why you're going to have in the Hamiltonian factor by 2. Then you're going to have K1, K2, so you can drop the vector signs, and you're just going to have I, and the I plus 1th will be, this is I plus A, I say I plus 1. So in terms of R, this is Ri, in terms of the distance, plus some distance A. In terms of the numbering of the position, this is I plus 1. And this is going to create some confusion when we look at, this. What are we multiplying this with? We're not multiplying with the number, right? We're multiplying with the distance, which is. So suppose A is 1. I guess, yeah, depending, okay, we'll probably take A as 1 or keep it as J. A is the lattice spacing. Okay. So you're going to have this, and you're just going to have I, and the first term will give you Ri K1 minus K2. Okay. First term is so this term is so Ri is the same. J is Ri plus A. So you're going to have this term times e power I K2A. K2A minus plus m. CK1 dagger C K2. Right? The Hermitian conjugate, on the other hand, will have a sign which is opposite. Okay. This is going to be the and you're going to have this thing. You can check this for yourself. This is correct. So you're going to get, so you're going to get, this is going to be minus t by 2n over k1, k2, and I. This is Dirac delta of k1, k2. And I'm going to take this, so this is cos k2a. So this gives minus t sum over k ck dagger ck cos ka. Right. Now this term is actually the energy. And why is it the energy? It's a simple fact. In the momentum space, you've written Hamiltonian in the momentum space, and you have diagonalized the Hamiltonian, the key basis. So there's only Hamiltonian, and the value of these diagonals are just minus t cos k. So here you have k as some value, k is not, you know. So this is a diagonal. When you act it on any state, you're going to get this as E, and this is shadow. Okay, so that is the idea behind why it is E, and therefore you have E of k is equal to minus t cos ka for 1D binding model. Now in 2 dimensions, as I told you, what you're going to have is uh, oh, there's space. So for 2D tight binding model, what you're going to have is do the same as what I've done, but now I'll just quickly do it. It's in the other notes also. 2D tight binding model. I, as before, means two tuple. That means I depends on, I means where your position is, right? That is, I has two numbers, which is A, B, right? Not A, B, P, Q. Therefore, Ci, the Hamiltonian which we had, is going to be, and these are vectors now, e to the power minus I, K1, R1 minus P2, Rj, CK1 dagger, CK2. Rj vector is Ri vector x minus a0, okay, in the x direction. And it is also in the y direction. This is in x direction, y direction. It's the same thing. So now I'm going to write the Hamiltonian. Expanded Hamiltonian. So my Hamiltonian is going to look like this. So my Hamiltonian is going to look like this. And this is nothing but this is going to give a delta function with this thing. So I have k1, k2, delta k1, k2, ck1, that is ck2. And this is this thing, this 2n cos k2x plus cos k2y equal to minus 2n k ck dagger ck cos kx a plus cos ky a. Therefore, E is equal to minus q by 2 cos kx a cos ky. That is it. This is in 2 dimensions. This is the time. Let me do two more problem. Yeah. So this is regarding density of states. Number 7. Let me do this first. Question number 7. Find density states for this is E of k minus 2 cos k. Can you plot it? This is for the 1D tight binding model where E of k is something like this. Find the density of states and solution density of states and plot it. So rho of E is actually the density of states, density of anything can be given as like this. It is given as like this. So this is similar to what you had earlier. Okay? There you had R minus R prime. So I have E minus some EK. Okay. Now assume that this K is the spacing between these K's is so small that I can take it to be continuous. Now this is a Lagrange system. Assume summation K can be written as integral dk, that is tends to infinity, and K spacing can be thought of as a continuum. Therefore, rho of E is equal to 1 by n integral dk E plus 2 cos k. Write 2 cos k as P, which implies k dp, which implies dp is equal to minus dk by sin k, which is equal to minus dk. Since it is a Dirac delta, there will come a mode and you integrate it. So rho of E is equal to 1 by n dk is equal to this is dk and this is dp. Then this is and since this is a Dirac delta, it should come with a mod, right? So this is dp mod this minus will go away in the other one mod p plus p and when I put p there, I have so 1 by n goes with the Dirac delta. This is my normalization. So I'll have this goes inside by root 4 minus t square. This minus c square. This is what my density of states is. I'm going to plot it something like this. Let me do one more problem. This is going to be problem number 8. Ah, So in EK, 2D side binding model, take Ax, ky nearly equal to 0, and using this, find A in this approximation and plot X, ky in this approximation. Now draw the full Fermi surface and plot it where plot of X, ky. This is the question. Solve it. So we had EK for a 2D side binding model like this. So I've taken A as one. So using the approximation, cos X can be approximated by majorly for scalar. Therefore, EK looks like 1 minus kx is equal to minus t 1 minus kx. Thus, you are going to have EK by t plus 1 equal to kx square. If you fix a EK in the kx ky plane, plot is going to look like a circle. And remember, kx ky should be nearly 0. This is valid near the origin. Anyways, for the sake of seeing it clearly, I'm drawing a circle around here. Like this. Yeah. Now this for this surface. Since you're going to